지난 시간에 리포트가 이렇게 나가 있었죠. 이거를 같이 한번 discussion. Last week we have a report. Number 1, we are to calculate the strain and curvature of a laminate beam with a rectangular cross section. While the sections, the beam is made of the aluminum in half, and the other one is steel. Let's try to drive the equations which we can calculate the strain and curvature. Well, I reviewed all the reports, and well, some are good and some are not so good. So I like to let's drive the solution together. Let's say we have a beam. We have a beam like that. And let's try to solve the equations for the laminate beam. This beam is subject to a we call in-plane load. The load is in the same plane as this beam. Let's call N. And another load we apply is moment M. And then we want to calculate the strain and curvature of this beam. Let's say we have a modulus E1 and E2, while each material is isotropic. And since those materials are isotropic, and also this beam is, this structure is assumed to be a beam. Beam means that sigma 2 equals 0. 2 means this direction. Let's call x2 and x1. So since sigma 2 equals 0, we assume that. That means that we can assume the Poisson's ratio equals 0. So all the material property we need is just Young's modulus E1 and E2. Now, while there could be several different approaches to solve this strain, but the most important assumptions we need to start with is the strain distribution. Let's say this beam, again, is subject to this in-plane load and moment. The strain, okay, this is the strain distribution. Strain distribution is assumed to vary through the thickness. Vary through the thickness means that the strain level can be something like that. And this is called epsilon x. Of course, in the opposite side, we'll have the same strain level like that. And by the way, this is the x1. We can we can assume or start with any thickness. This can be a H1 and H2, but let's make it simple so that the bottom one has the thickness of half H, and the other one is also a half H. But the procedure can be easily generalized and to cover many arbitrary thickness. The reason we need to go through this process is that all the design of a composite laminate will be based on the same assumption and same very similar solution we will have from this example. So we need to, this problem is so important, very important for us to understand the behavior of a laminate composites. And again, we are solving the structures, not the elasticity solution. But elasticity solution and structural solution is different. I like to say elasticity solution and structural analysis is not exactly same. Elasticity solution is based on all the equilibrium equation, three equilibrium equation and three equilibrium equations and 6 stress-strain relations and 3 compatibility equations. So totally we have a compatibility equation, and there is also another 3 strain and displacement equations. But structural analysis is different from elasticity solution in that we assume some stress component, something like this, and we assume assumption on several stresses. Otherwise, these equations, this is a totally 15 unknowns, and 15 equations and 15 unknowns. This is the equilibrium equation. So as you can see, there are 15 unknown displacement, 3 displacement, and 6 strain, and 6 stresses. So 3, 6, 6. So 15 equations and 15 unknowns, so that we can solve the problem. Well, this is the very ideal cases. But solving this equation involved solving partial differential equation, which in many cases is impossible to solve as an exact form. But very importantly, in real structures, such as a beam, such as a plate and shell, beam and plate, or shell, there are some components are very small. So we are able to assume some stresses are 0 compared to others. not exactly 0, but quite small enough to be neglected. And this assumption makes the solution very easy, and process is easy to follow. So we need to clearly understand the fundamental difference between elasticity solutions and structural analysis. We, as a designer of the structures, we need to understand the structure. We need to study much about the structural analysis, such as a beam analysis and plate analysis and shell analysis, and so on. While this one is the, of course, is a one-over beam. And in this beam, even though this is a beam type, of course, there are 3 equilibrium equations and 6 stress-strain relations and 3 compatibility conditions and 3 strain displacement relations. But here, the assumptions of the several stresses is that not just a sigma 2, but also sigma 3 and sigma 4 and sigma 5 and sigma 6. These are all shear terms. This is the shear terms. Well, sigma 4 is sigma yz, and sigma 5 is xz, and sigma 6 is xy. We will discuss later, but this beam theory, we start with these assumptions. Okay, so these based on these assumptions, so only non-zero stress is the sigma 1. Sigma 1 is the major one, and again, others are very small. And this is the structural analysis. So in this, to solve these equations, based on these stress assumptions and also strain distribution, this is the most important step in structural analysis. Again, in structural analysis, we need to start with a strain assumption. Strain assumption means that we assume strain distributions. In this case, the strain of the sigma x, I'm sorry, the sigma 1 and sigma x is the, we mean the same thing. And 1 means that x, and 2 means that y, and so on. So sigma x, epsilon x, are assumed to vary linearly through the z direction. This is a z direction or x3 directions. So epsilon x, now we need to write down as equations. Here I want to emphasize again, depending on the simplicity, I interchangeably use. Sometimes we use the 3 as a z, and xy as the number 6, and so on. We will discuss later, but just please understand, x means the 1 direction, y means 2 direction, and z means the 3 direction. So x3 is the same as a z. So now epsilon x is the major strain along the beam, because this is the x1, and this is the, we can call x. Epsilon x is now, since it's assumed to vary linearly, we can call epsilon x0, which is the constant, and plus and z times curvature. So here, z equals 0, this is the important. And again, epsilon x is the function of z, and z is the here, and we have a two constant. So this is the strain distributions assumptions in structural analysis, not like elasticity solution. Elastic solution, this is not quite true, but again, structural analysis. So we only have a concern. We only want to solve the major component. Okay, I'd like to select this. Okay. So in this procedure, it is important, where is z equals 0? Where is the z equals 0? Since we assume this strain is a function of z, so we assume that z equals 0 is the half of the thickness. Half of the thickness means that here, this is the x, and here is a z, and here is a h over 2, and here is the h over 2. Doesn't look like exactly the same, but here is the bottom thickness. Okay, so in this distribution, we can visualize, we can divide into two terms. It's like uniform strain, which corresponding to these terms, and plus zk means that we have something like these kind of terms. Okay, so uniform strain and purely linearly varying terms. So epsilon 0 is this one, and zk is these terms. And z equals 0, okay, this is the z equals 0. Now, the stress strain relation, simply sigma x equal E epsilon x. So this is the E epsilon epsilon x is this one, and epsilon x0 plus z and k, and this is the sigma x. Now, what we have, the load we apply on this cross section is the N. This is the axial force and moment. These are moment we apply to cross sections. So by definition, what is N? Well, N is the this sigma x which are apply or distribute the cross sections dA from bottom to top side, and very importantly, sigma x we don't know. We don't know how this distribute. We don't know how this sigma x distribute. We cannot assume how sigma x distribute through the thickness. That depends on the material property. Only assumption we can make is on the strain distribution, which varies linear. Okay, this is so important. Most of the structural analysis, we start with strain distributions. Okay, please don't forget, we start with strain distribution. This is the actually same as the displacement restrictions, but we will call it strain distributions. Anyhow, sigma x we have here, so we can integrate help of h, and here E, Young's modulus, epsilon x0, which is a constant, and z and k. And now, what is the dA? dA means that cross sections from bottom to I mean any cross section. So the dA say dA we can call z, and here small dz. So this is corresponding to a dz. So dA will be dz multiplied by the width. This beam has the width, let's call B. So dA cross section will be dz times B. So instead of dA, we can say B times dz. Now we just integrate this equation, but very importantly, E, which is the Young's modulus, E is not the constant. Why? Because we have E1 and E2 different material. Well, in general, we may have many different layers depending on the layer sequence, and we can call them, we can take this E as the function of Z, okay, function of Z. E is a function of Z. So we cannot just directly integrate, but we can just integrate from here to there, because all the material property of E will be the same. And then this upper part can be separate again, and then we can have another E. So this one integrate and 0, and E will be Young's modulus E1. Let's call steel. Let's call aluminum. So Young's modulus E, let's call E steel. And now epsilon x0 plus z, k, and b, and dz, plus upper one, we have E aluminum and 0 to H over 2 and epsilon x0 plus Z, K, and B, dz. Okay, so this one, now we can easily integrate E, ST, and this one, since it's a constant, and E epsilon 0 and B times the thickness here, so this will be half H plus, now Z we can integrate, so integrate means 2 over H Z square half to 0, and then there's a K and there is a B like that, and similar terms here. Okay, so we can continue the derivations. So N equal E steel and epsilon x0 plus B half H, and this one is what, 8 H square, and oops, this is the this is multiplications, and this is a K and B, and same E aluminum and epsilon x0 and B times H, B times half inch, and also 8 H square and K and B. Okay, so this is the one equation we can have here. Important point here is that this is the N, the in-plane load we apply, and this is the strain, in-plane strain, and K, and in-plane strain, and K. Other terms are all known factors. And now, similarly, we can derive the moment by definitions, and the H over 2. And now sigma x times moment by definition, sigma x times Z has to be multiplied, and dA. So H and sigma x is given is x0 plus zk, and then z, okay, we have a new terms of z because the moment we need to have the z, and b dz. So we just integrate them, okay, integrate them, and separately, bottom one and top one, and E times, again, ST. Now we have a Z here, okay? We should not forget we have a Z, Z here. So half and 0, and then epsilon x0 plus zk and b, and z here, and dz plus E aluminum, and 0 half inch epsilon x0 plus zk, and b times z times dz. So this one, this integration can be easily done. Say EST, and here epsilon x0 and z is here. So integrate, what do we get? Well, we get epsilon x0 plus, well, there's a b there, and this is a half inch. Okay, so 8h square, right? And plus z, here we have a twice of z, and times z. So k and b, and third, and so 12 h third, and plus aluminum, and the epsilon x0 plus, no, not plus, we have a b, we have a h square 8 plus k and b, and same and right? Oh, there should be a minus here, because we have a minus here. I mean, these terms comes from z square, so integrate means z third, and minus half inch 0. So oops. So this is the not 12. This is a 24. Right? So there's a third power. So that's why we need to have a minus here. Okay. So here again, we have a moment, and we have a epsilon 0 and curvature, and epsilon 0 and curvature. Okay, and now let's simplify it a little bit, and these terms EST and B times half H, and then the other term here, E aluminum, and B times half inch will be epsilon x0, okay, plus, and then here is the same, EST and B half of, no, this one, ST, and the H square and B plus AL aluminum times 8H square and times B and curvature. Okay, so this is nothing but, you know, we have a same terms, epsilon 0 and K. And now moment, EST here and times B, 8H square, and we also have epsilon x here, plus E aluminum and B times 8/H square, and then epsilon x0 plus now the curvature terms, so minus EST B times 24H third plus E aluminum B 24H3 and then curvature. Okay, so this is the terms and moment. We have epsilon 0 and curvature, and this is a moment and epsilon 0 and curvature. But let's see, there is a minus there. Doesn't look like that is right. Minus where, let's go back. And here, moment, something like that, Z square. Oh, this one should be plus, right? This is a 0 minus, and there's another minus. So, yeah, I knew there's something wrong. Okay, so this is the 0 minus half of H, so this has to be a plus, right? Okay, so this has to be plus. Okay, so now we went through a little bit of a derivation, but the most important procedure, starting point is that the strain distribution of these. Okay, I would like to emphasize the strain distribution of these, and then a definition of the in-plane load, and this one, you know, definition of the stress-strain relations, right? This is the second most important equation. And third one is the this definition of an in-plane load and definition of the moment. Okay. So let's as a final, I would like to summarize as a matrix form. Matrix form means N and M, in-plane load and moment equal. Because as you can see here, we have same terms, epsilon 0, and K. So it is a 2x2 equation, right? We need to solve, we want to solve this epsilon 0 and K. And so this is the 2x2 equations. And here, EST and B and half H plus E aluminum and B and half H. And this term, the second term EST and the 8, I will write B first. B times 8H square plus E aluminum and B times 8H square. And then EST and B 8H square plus E aluminum B 8H square. And the last term EST and B and 24 H third plus E aluminum and B 24 H third. Okay, and then in matrix form there's epsilon x0 and curvature. So this is the final form. Okay, so as you can see, these are given. These are given, and all the material property. Okay, material property is the this guy. These are material property. And the last known value is the geometry. Is a geometry. And then what to solve? We want to solve this strain. Epsilon 0 is too red. And I just use this one. So these are the unknown to solve. So it's very important to notice here that always the structural problem. Oops. Structural problems, we need to have a given condition. Given, what are the given condition? What are the values we need to know? We always need to know geometry. We always need to know material properties. materials, we always need to know force. These are three terms we need to have to solve the equations. So as you can see, these are force, okay? So this N and M is the force. And geometry, what is the geometry? Geometry is a thickness and width. So that is the geometry we have, same value here. What are the last one? The last one is the material property. Young's modulus is the last one. So I like to emphasize that in any structural problem, we have to have the known value or given value, which are geometry or dimensions and material properties and forces, which are applied to this geometry with this material property. And then we can solve the a strain or deformation. As you remember, epsilon x, which is the function of a z, now is assumed to be epsilon x0 plus z times k. So out of these equations, we will have these. We will have these terms. Right, this term and this, and which is the AAK here. So once we have epsilon x, we can simply calculate the EX stress using the stress-strain relations. So these are the equilibrium equation and assumption and so on. Anyhow, this is the very straightforward, and this procedure can be applied to many different layers, not just a 2-layer, can be applied to 3 or 4 and any multiple layers. So this is the equation we need to solve, and we need to program. Always, we have to have our own tools, which we can use to solve the problem. Of course, to reach that one, we always, we have to have an algorithm. In this case, this is the final equation, and we can call it a algorithm. Now I like to copy these terms. This is the result in Excel. Let's try to make a simple Excel so that we can easily calculate the values given the given this value, geometry and material and forces. Okay, so first of all, let's say we have a geometry value. As a geometry, again, we have, what do we have? We have a B as a width. We have a H. We have a H as a height. And also we have a material. As a material, we have a steel, Young's modulus of a steel, and Young's modulus of the aluminum. And last one is the forces as a in-plane load N and in-plane moment M. So these 6 numbers are given. And in any programming, while Excel is also considered as a program, in any program, what we need to start with is define the input values. What are the input values? These are very important steps which will help us to develop a tools or any program. Sometimes this variable better to have some meaning. So I'll just call h as the height. And this is okay. And this is the, I will call in plane load. And this is the call, I will call bending. Okay, so let's type in these equations. And how about the values? Well, B widths in dimension wise, let's always consistent with length as a meter and force as a Newton. So B widths, I would say 0.1 meters, and H can be 0.2 meters. And Young's modulus, still, I would say 200 gigapascal. And aluminum, I would say 70 gigapascal. And in plane load, well, how much force we can apply? Let's say we apply, well, 1 ton, just a 10 to the 4, and moment, since the height is a 0.2, let's say just 100. Okay, this is the just arbitrary value we picked to just get some numbers. And now we have these equations, and for this 2 by 2, let's define this one as the 2 by 2, which will have these terms. And here we will have these terms. We will have a 2 by 2 matrix here. So let's say equal, and we wish to type in the symbol as we define here. Of course, the computer or Excel cannot recognize still, I mean, this value. So it returns, what is this name? So we like to have this value has the name of this. So this one, simply you type B widths. Okay, so 0.1 will have the name as the B widths. So anytime, let's say B widths times whatever value, you get the values. So whenever you change this value will be automatically changed. So it's convenient to define the names. So we have this series of a name. The easy way to assign the name to each column is that just select like that and select from a selection to name. So it's automatically detect. Left column will be given as a name. So say okay. Then what we need to do is that very conveniently we just follow this equation as we drive. So E still times B as a width times H as a height divided by 2, right? So this is the first term. And now we have a second terms. We can simply copy and paste, and we change the aluminum. Okay, so this is the value. Is too lengthy, so I like to change it to scientific values. And the other terms is similar, so I just copy and then change it. This one as the H height will be power 2 and divide by 8. And also, what is this? Second, B, H, and divide by 8, right? And notice that this term and this term, they are same. Well, there is a very long story that this always a structural analysis term, they have to be symmetric. Same as in finite element method, always the this kind of a structure representing matrix has to be symmetric. So anyhow, the last term will be a B as a third, and this term will be 24, and this term will be what? 3, and this term will be a 24. Okay, so this is the equation, and now N, how much N you apply? N, you apply this much, this one you apply this much. So this is the N and M, this is the matrix. Now what you wanna solve? You want to solve these two terms. How can you solve this one? Well, here you can just to solve this one. What you need to do is to just inverse of this matrix, inverse of a matrix, and multiply here, right? Inverse of this matrix and multiply by this. So you do the exactly same, and and M mult and M inverse of this, and multiply by this. Okay, so it's automatically invert 2 by 2, and then we get the solutions. So this is the nothing but the strain. Okay, this is the a strain. So whatever value you like to have, let's say you have a same value. Let's just copy this value. I may save it. And let's say this one has the same material, you will have this. And if we don't apply any in-plane load, as you can see, there are very small strain terms. I thought this has to be more small. Oh. Okay, well, this one have to be same. I mean the 0. Why not 0? Okay, there is a mistake. You know, we in derivation we always make mistake. Here, this term looks not right. As a verification, we always need to verify either our derivation, either our programming. And as you can see, we assign the same material. We don't apply the in-plane load. Then we should not have a in-plane strain, right? This is the in-plane strain, EX, I would say 0. This is the K. And curvature. I will cut and paste, and this one. Okay, so I'm sure this term has to be minus there, and let's get back to our equations. Okay, when we drive here, I'm sure we made a mistake. Where is a mistake? Here, when we drive, okay, in previous slide, when we drive here, and then there is the 0 minus this. So 0 minus and square. So this has to be a minus, right? So this is not right. This has to be minus because this is the minus. Same here, and here 0 and oh, yeah. So this term will be minus, and so this has to be minus, and also this has to be minus. So curvature, and also another mistake we have here, Z and minus, we have to have a minus here, and also have to be a minus here, right? So here is the minus, and here is the minus. No. And this is a minus, but this is not the minus, right? This one integrate, and this and plus and plus, right? This is the plus. Sorry, this has to be a plus. So this plus is correct. Plus is correct. And moment, this one, there is the minus. So there should be a minus here. So this is the minus, and this is the A plus. So aluminum, still here we have a minus sign, and still we have a minus sign here, okay? So still we have a minus here, and still we have a minus here. Well, we don't mind going through this kind of debugging. We always have to, face this kind of debugging procedures. So back to here. Well, here we have a minus here and minus here. But as I mentioned, this term and this term is always the same. Now this term, we have to have a minus here, and we have to have a minus here. So now, as we expect, the strain, in-plane strain should not be non-zero, should be zero. In other words, let's say we have a cross-sections like that, and the same material, for example, steel and steel, which means that just one material like that, right? And subject to only a moment, and moment, then stress will be always is something like a like that, right? Okay, so here at the center, in-plane strain is 0. Okay, it seems to be correct. Now, one more step, one last step is that we plot this strain. We plot this strain. How can you plot this one? Well, as we have it, epsilon x is the epsilon x0 plus z times curvature. So simply epsilon x and z is the linear function. So let's, this is the ex, which we're gonna plot, and this is a z, a coordinate. And so z coordinate, z starting with what? The bottom one is the half h, so minus, so this bottom coordinate, okay, bottom coordinate will be h height divided by 2, and then let's say we have a delta, this one plus, let's call height, oops, height times divided by, let's say 20. Okay, then let's say 18, 19. This will be a from bottom to top, okay? From bottom to top, and epsilon x, I will call this one as the z-axis. And the z-axis, as we already noticed, we can click this, and this term will be a coordinate, and epsilon x. Now, as we start with from this here, this equal, we got this value, right? Epsilon x0 plus a z coordinate times a curvature here. Then automatically epsilon x is calculate, and then we can just select them. We can go to insert. We can go to a plot, and we can plot them. This is the a strain. This is the a z coordinate. Okay, this is a z coordinate. This is the strain. This is easier to understand. I will change this value into a scientific, so that it is easier to note. Okay, so this is the strain. Now it's easier to for us to understand, and now we can enter this aluminum, say 70 gigapascal, and you see what will happen. And what will happen is that this at the zero, we have some strain here, and neutral. This is called neutral axis. Neutral axis will move to a little bit down, because the bottom is the steel, top is the aluminum, and bottom, the steel is a little steeper than bottom. So we can see the neutral axis move a little bit. And the if we apply the in-plane load, of course this moved a lot. As a zero, we have this much strain, and the of course, if we don't apply any bending moment, and then we have a same material. We apply only in-plane load, while strain will be uniform, right? Obviously, this is the epsilon x. Now also we like to calculate sigma x. What do we need to do? Well, we need to multiply. This is the epsilon x. And sigma x is simply we multiply Young's modulus. So how can we calculate? Well, we simply multiply Young's modulus times, the strain x times Young's modulus. But Young's modulus is not the constant, it varies through the thickness. So what can you do? Well, if a z coordinate is the less than zero, then the material property will be a steel. Otherwise, we take the aluminum. So this will be automatically like that. And as you can see, let's try to plot steel versus the coordinate. So this is the stress, epsilon x. Now let's play with some value. And this is the aluminum, 70 gigapascal. And as you can see, how these stresses are suddenly changing. And if we apply the moment, only moment, and no in-plane load, what will happen? Well, as you can see, here has the, okay, let's just take a look at this pure moment, and the same material will have a same linear strain and linear stress, no doubt. And again, if we have aluminum and steel, the stress, even under the moment, the slope will be different, because upper we have aluminum and down we have a bending, and we have the neutral axis located here. Neutral axis here, so we have this much stress and this much the stress distributions. So when you have a play with Excel, I highly recommend to have a different value for the input and output, as the value has a different color, so that we can easily follow. Well, this is the a procedure. We don't have to pay much attention. So this is the and also this can be like that. And in PowerPoint, when you report as an engineer, we always need to have well documentized. We need to have a clear definitions and clear results. So if you program well, all you need to do is just copy and paste. This is the input. This is the output. And this is the plot, for example. Okay, so as you can see, you can do a lot with this Excel for many different thickness and load and material properties. I hope that you guys have the same results. Doesn't have to be same derivation, but I hope that you have the same results. Okay, so this is the one. I mean, what we cover for the report one. I spent more than 1.5 hours, because it is so important to understand the strain and stress distribution in a layered beam, because the layered beam is the fundamental basis for us for our understanding of the laminate composites. Okay, so we will have a 10-minute break. This is the 2:30. Our class will start at 2:40. Okay, thank you. See you soon. Okay, let's continue our class. The Excel file we just developed, save as a report one, has been passed to all of you through KakaoTalk. You can notice. Please take very close look at it and try to understand how we program. Well, I will call it programming in Excel. This kind of procedure is very important. Okay, and for those who do not have much experience in Excel, please go through all the steps, very detailed, using this Excel and using the video clip, which I will upload as well. And please learn as much as you can. It's very important, and not just for this class, for other engineering problem as well. Okay. Today, as a continuation of the last class, we had a we briefly reviewed the fiber property and resin property and so on. Today, I'd like to go through micromechanics. Micromechanics, what does it mean, and why do we need to understand micromechanics in these composite materials? Okay. Micromechanics, well, as it says, mechanics, but for very micro scale constituent. Before we go through micromechanics, I would like to briefly introduce the multi-scale analysis of composite structures. Let's say this is the macro level, macro scale. This is, I would say, a structural level where we define the geometry, we define the material property, and we under certain load. Okay, we like to calculate the strain and stresses. And here, once we have a stresses, basically, we need to calculate or how much the stresses we have in a toe. The toe means that in composite, before we have one small fiber, we may have a toe has the a bundle of fibers. Okay, these are a bundle of fibers, and these are a bundle of fibers, and which is called mesoscale, and microscale is just one fiber, and then we can get some stresses at the fiber and matrix, and now we have a stress-strain relationship of the fiber and resin. And we can go through, we can apply a material property for each constituent, matrix and fibers, such as the SN curve, such as the stress-strain relations. And since we know the stress level in each constituent, what we can do is that we can degrade the material property depending on the stresses. And then once we have a degradation, the stress distribution will change depending on this damage level and depending on this, for example, SN curve for the case of fatigue. So once we have a degreed material property, we can have another material property, which also can be derived using the micromechanics, and then we can update the material property of the composites. So this is the big pictures of multi-scale analysis of composite structures. And now let's just focus on the micromechanical models. Okay, forget about this. This is the, by the way, the Ubun. I'd like to introduce the concept of the toe. We don't have a, let's see. We don't have a slide of the toe. Okay. It is important to understand the concept of a toe, okay? Okay, toe means that once we have one fiber means that, for example, here you see one tiny line, one small line, that is the fiber, and this whole bunch of fiber is sometimes 20,000, sometimes 40,000. Instead of 1,000, we call K. So sometimes 20K fibers, sometimes 40K fibers. So this whole bundle is called toe. Okay, this is a toe, and so when they produce the carbon fiber, they just have a toe red over the bobbin, and this is the cell. They sell just by this bobbin with fibers with the toe. Okay, it says the 1K means that this one toe has the 1,000 fibers. Okay, and the so you can see many different types of the toes. And carbon fiber, Jortec is the one famous company producing carbon fiber. They have a PX35, and PX35 is the known for very large toe. Large toe means that one toe has the 40,000 fibers. It's very heavy toe. Okay, a lot of fibers in one toe. So that is a toe. But when we have a composite, we have a prepreg means that we have this kind of prepreg and the this kind of toe. Okay, toe will be a spread. Toe will be spread. So this is the one toe and second toe and third toe and etc. This is the very typical form of the prepregnate. So that's why a prepregnate fibers. So it's a prepreg. So a toe has the spread, and the resin is the impregnate. So this is the prepreg. So I like to say here has the prepreg This is the bobbin. So again, this is just one fiber. Okay, this is just a size of a hair, human hair, to compare to emphasize the how small this fiber is. So this is the one fiber, and 20 times or 40 times is the a toe, and then we have either a spread and either this kind of open. Okay. This is the just one filament fiber, and diameter will be like about 7 micrometers in case of the carbon fiber. Glass will be is a little bit thicker, like 12 or something. And this is the bobbin they produce. So this is the about the 20,000 fibers. So this case we call 20K toe, or sometimes 20K fibers. This will be called 24K toe, and etc. And now these fibers can be spread and resin impregnate. So this is the toe, spread it, and plus resin impregnate. As we call it B stage, not fully bonded, just half bonded, and then spread it. And this is the one things. And another form is that this is the woven fabrics. So this one has the interchanged toes. Okay, so this fiber again, they sell this kind of a bobbin. Let's call a bobbin. Bobbin, what they sell by the pre-preg. They sell by the woven fabrics. Okay, so we buy this kind of a composite product, and we mix some products. Say this one is the filament winding. Such as the pressure vessel. This one is the most high quality, and this is the layered, and then autoclave, and I would say aerospace structures. And this one is the woven fabric process. It's not much special process, but this is the called wovening process. By the way, there is the another one. Another one is called stitching process. See, this case, we have a small stitching yarn, and stitching yarn, we stitch each spreaded toe, and we stitching them. Okay, so this is the called NCF. This picture is better to understand. So this is the non-crimp fabrics. So you call NCF. So when we buy the composite and then make some part, we either buy the bobbins for filament winding, and this kind of pre-preg or woven or this kind of NCF. We need to understand this process. Let's say, since we are introducing this different form of the composites, we can easily go through. So this one is the NCF. Oops. Well, this is the Lamborghini using the NCF of the Sartec, and as you see in the background, you can see the all the fibers are stitching. Non-cream fabrics. So each poles are stitching, but no resin yet. no resin yet. So once we have this dry NCF, and then we infuse some resin, and this is the NCF procedures. Okay, so this is the NCF. Actually, I like to introduce how they are produced. Okay, let's say video. I like to emphasize the how is the toe is the spread. You know, spread procedure is important. Well, there is not there's no video here. There was some. So it's not, you know, difficult to understand. I'm sorry. Okay. Let me go through this one. Okay, this is the process to make a roof of the BMW, I think the i3. So each one we have a NCF toe, I mean NCF fabrics, and sometimes just woven fabrics, and depending on the design, we layer them. As you can see, you know, each stage we have a different layered. I like to emphasize that. You know, depending on the design, again, we have a NCF, we have a woven, we have a, you know, many different, even woven or NCF, we have a different angles. So it's just automatic layered, and then we have of course we have a design, and we have a layered. This is the roof of the so this is a layered dry fabrics. And a robot is picking up, and we have a mold, and we have that dry fabrics over the mold, and then we have a resin. Now you can see this is the a final product for the roof of the BMW i3. So we can have a many, yeah, this is the one, just a roof BMW produce. But again, I like to, okay, this is how they cut. But we need to understand how they make this NCF or wovens. Because it is a very sensitive technology, and I'm not sure they don't produce, I mean, they don't show the process, the making of new carbon. So, but I'm sure the oven, there will be a process called well, they don't show much about the production line. But anyhow, it's not so critical, but the point is that this is fiber and bobbin, and then we have many different process. Like here we can have a spreading, we can have a woven, we can have a NCF. Of course, this one, this is how they make a carbon product. And the reason I'm explaining so much about these carbon things and layered and so on, this is the typical cross sections of the composite part. Let's say we make a roof, we just watch through the video, and this is the cross sections and certain layer. This is just one layer. You can imagine this is the prepreg UD, and this is the cross section. Let's say this is a one prepreg, just one prepreg with one angle, and say typical thickness is the about 0.125 millimeters. And imagine how big this fiber. This is one fiber. One fiber is let's say 7 or 8 micrometer. So 0.125 will corresponding to about the 15 to 20 fibers. So, well, you can imagine 12K can be spread as much as a 10 millimeter wide. You can easily count them. And now this one needs to be assumed like a square array and hexagonal array or diamond array, depending on the situations. Well, we touch this diagram, and now each one we assume is called unicell. The arrangement are a little bit different, but the one thing for sure is the same fiber volume fraction. Okay, same fiber volume fraction. Fiber volume fraction. Understanding fiber volume fraction is a very important. No matter what model we have a same fiber volume fractions, which is called often called VF. So each one we call unicell. Unicell means that this is the one cell, and this is a repeating, and this is how we the representative volume. Now, in fact, there are several different types of micromechanical models, and one just we just seen here. We can assume, we can derive the equations for using analytical solutions. What it means that, you know, all the each unicell, we have a fibers and resin, and this unicell will have to deform together, and there will be some equivalent material property, and there will be some stress concentration because of this fiber inclusion in the resin. So there are many different ways of calculating interactions between the fiber and resin. So there are solutions, is called analytical solution driven by the chamis. And another one is that where we just using the finite element assumption, either scale is this one. This is the scale model. This is the hexagonal models. And also there can be, we can assume very simple models called a simple rule of mixture. Rule of mixture, what does it mean? Well, since this arrangement is a little bit difficult, we just assume that there are only fiber and resin layers, okay? So forget about all the circular inclusion. We just assume that one by one arrangement, fiber matrix, and so on. We just assume like that. I mean, similar to this one is the another solutions called, this is another analytical solution. This is the enhanced rule of mixture, EROM. I'm using the octahedral. This is the fiber has an octahedral, so OFM. And this is the developed by the our lab. And this is the much more accurate than this, but we don't have to use the finite element method. We drive the analytical solutions. So there are several choices to calculate for the micromechanical models. And what does we do with the micromechanical model is that, let's say this is the one prepreg toe or something, and or you can say some region in the fiber arrangement. And micromechanical model, this is the cross section, and what's happening inside is that in the composite, this layer will be subject to many different loads. The load, like, you know, epsilon y directional stress and x directional stress, and mainly shear stress, and sometimes temperature. These are applied to this kind of a unicell arrangement to a unicell. And the now this one, just one unicell, we assume that this will subject to a same load as the this outside. So again, this is the a unicell model. Unicell micromechanical model, where we have fibers, we have a resin. What we like to do is that sigma bar is that the stress we apply, okay? Now this is a very important concept. Sigma bar is the stress we are applying to a macro, ply level, okay? This is the ply level. And micro stress, there is how much the relation there will be. So each stress, local wise, in any point, we have many points. We have many points, and we have a sigma bar, and there must be some relations. So again, this is the sigma bar, which is a prime or macro stresses, and sigma x is a function of x means locations. We could have many different stresses for the given sigma bar. Many stresses means that we have many different amplification factors. Amplification factor means that we have all different color. You know, color shows that level of amplification. So we have this is a linear relations. This is a sigma bar, which is the macro, and sigma is the micro stresses. In the sometimes is a fiber, and sometimes is the matrix. Can be here or can be there. And also there can be some delta T, which is applied in the level of a macro. And also this delta T, when we have a delta T, there will be some stresses is caused inside depending on the position. So AX is the also we call stress amplification factor for the temperature increase. And again, M is the most important stress amplification factor for macro stresses. Okay, so that's the concept of the amplification factor. So through micro mechanics, we like to have these stress amplification factors. This is how we get these stress amplification factors. Well, again, why these stress amplification factors are so important? Well, once we have these stress amplification factors, to calculate these micro stresses, what we need to do is just nothing but multiply M by sigma bar. Then you can immediately get the sigma local stresses. So that's the concept of the stress amplification factor. And the this is the more in detail, depending on the position. So as you can see, we have a K. You know, K means the location. K represents the location, and sigma bar means that a macro level. This sigma bar is the like load we apply as a to the unit cell, but this is the same as the macro prime level, and this is the local stresses. So in matrix form, we have a 6 by 6. So this is the local, and this is the a macro. And delta T as well. And also, very importantly, on the surface between the fiber and resin, you know, we always have a interface between the fiber and resin along this interface or along this interface. We need to calculate the stresses at the interface. Interface, we always have the 3 component and normal and 2 component of tangential components. So very similar to this stress amplification factor, we have a macro, we have stresses at the interface, we have a 3 by 6 component. So through micromechanics, what we do is that to calculate this M matrix. Okay, that's the what we do at the in the micromechanics. So this is the some values at the interface. Okay, and these are some stresses at the stress amplification factors. Stress amplification factor is not the constant value. constant value. For example, when we apply the sigma 2 equal 1, sigma 2 bar is the macro, okay? There are some little confusion of the symbol, but this sigma 2 bar is the transverse load. And then we can have a sigma 1, sigma 2, and sigma 3, and sigma 4, and so on and so on. Again, under sigma transverse stress is the sigma 2 transverse. We can have a 6 component of stresses. As you can see, among these, 2 of them are 0. Only these 4 of them are non-zero. And this color, what does this color shows? What does this color represent? So as you can see, we are applying the sigma 2. Okay, this is the important concept to understand micromechanics. And we are applying this sigma 2, right? Only. We don't apply this guy. We apply only sigma 2 bar. And then stresses at a certain point, the stress component we will have will be just multiply this and then these terms. And if we apply unit value 1, all these stresses we calculate will be this value, m values, right? 1 multiply this. So all these stress component we can calculate under sigma 2 equal to 1, then this color represents m. This color represents m12. This color represents m22, and so on. Well, there is a no, 0, 0 because the FEM shows that no value. So we found from FEM. So this is how we calculate this all m value. And the concept of a single model needs to be well understood. This one is not just one fiber. This represents a multiple model. So when we calculate this stress amplification factor or M distribution, we need to apply the same boundary condition as noted here. Here, see, we have this guy, and here is this guy. So, for example, this is not, it's a no free boundary condition, because this is the symmetric. This is the no free boundary condition has to be a symmetric boundary condition, for example. Okay, so this is the concept of a unit cell, and now we can get the many different types of stress amplification factor depending on the unit cell models. You can have a square, you can have a hexagonal, you can have a diamond. And we confirm the accuracy by compare with polarized light experimental measurement. And this is the actually one unit cell calculate as you can see here. This is the one unit cell calculation, and as you can see, these are repeated. Right? So And then we can calculate the strength, how much strength we will have based using these stresses and using the material property of a resin and fiber. Once we have a stresses inside the resin or inside the fiber, there is the failure criterion for example, for the resin. This is the failure index, failure criterion for the resin. Okay, this is a failure criterion. We have all the stresses in the resin. We can have the failure index in the matrix. Okay, so as you can see, failure stress failure index is reach 1.55, meaning that if we know that resin tensile strength, transverse strength is about 64%. So transverse ply strength is the lower than resin matrix because of a stress concentration. So this is just one example. And this is the another example for compression. See, it's the same. This is a tension. This is a compression. Only sign is different, but this one, Y prime is the transverse compressive strength. Can be calculated from tensile strength of a resin is 2.7 times higher. So compressive strength, you can see 2.7 times higher than resin strength. So I don't want to go in detail, but this is the how we make use of the micromechanics. And in fact, to calculate all the components, we cannot, considering all the points is too much. So we just select some point, and then that's the those are points we calculate for stress amplification factors and so on. So these are a basic concept of the stress amplification factors using the micromechanics. And another important concept is the, it doesn't show here. Another very important concept of the micromechanics is to calculate equivalent stiffness, which is often called homogenized material properties. I'm sorry, I don't have that slide. Okay, here. Another important role of the micromechanics is that is the calculation of effective stiffness or homogenized property. What we do is that, again, the this one, well, this one we can say that, for example, we're gonna use this one as the unit cell. Well, this is just a representation of the how we apply load. So let's say we have some unit cell and there are stress and strain in macro level. So what we like to have is the this macro level stiffness matrix using fiber material property. So given fiber and matrix of stiffness, we calculate the C bar, which is a stiffness matrix. Once we have invert that, we have all kinds of engineering properties. This is a homogenized property. So input will be fiber matrix stiffness, and the output will be the engineering constant. Well, again, how can we do these procedures? Actually, what we do is that first, how do we calculate this 6x6 matrix? Well, we need to calculate the 6 times, and first time we apply the unit 1, 0, 0, 0, 0, 0. So we apply this procedure means that this reaction, all the reaction stresses and the boundary will be this term. So we apply 1, 0, 0, 0, and reaction will represent this column. And second calculation, we have a 0 and 1, 0, 0, 0. We apply the boundary terms. Reaction will be a second column, and so on and so on. So 6 times iterations, and then that's how we get the C matrix, and we invert. Once we invert, and then what do we have? We have epsilon bar and the S matrix and sigma bar, right? So S matrix is the inverse of the C matrix. Okay, so once we have a S matrix, then this inverse of the S will be a epsilon 1, and inverse of this, and Poisson's ratio, and so on, so on. So this is very important to understand. So micromechanics has two different roles. One is the calculation of a stress amplification factors, and second, we have equivalent stiffness. That's what I meant by here. That's what I meant by the homogenized stiffness. Let me delete all of this writing. So what we need to understand from this micromechanics is that just two concepts, two most important concepts is that using the micromechanics, we calculate a homogenized stiffness, and we get these stress amplification factors. Okay, more specifically, we calculate the C, we calculate this M, and if needed, we calculate the A. Of course, from this C, we get the S bar, and we get all the epsilon. I mean, Young's modulus X, EX, EY, and Poisson's ratio, and so on. Well, I'm sure some of you do not have idea, don't have any idea about the EX and EY, well, don't worry. We just take them as the stiffness. So we will cover them. We will cover them in this class. Okay, so please just have a concept. What do we do with the micromechanics? What do we do with this unit cell? Well, purpose is that homogenize the material stiffness of apply and calculate the stress amplification factor. One more step. What do we do with this stress amplification factor? Well, this one applied to a strength of the resin and a fiber. What can we do? We predict the strength. We predict the strength of the UD composites. Okay, so as a result, to make a long story short, what we like to do using the micromechanics is that we get the stiffness, we get the strength. Where strength we will cover later in the X directional strength, fiber directional compression, and Y prime and S. Those are strengths we can calculate. What are the input? What are the input value? Well, input value will be a fiber, resin, stiffness, and strength. Okay, so these are a very important concept. Again, we don't have to use this fancy micromechanics. We can use alternatively. You can use very simple, simple form like here. We can use a very simple analytical equation. We can use the very simple rule of mixtures. You can use the some little sophisticated rule of mixture and so on. Okay, so understanding micromechanical model. Each one anyhow represents unicell. Okay, unicell, not the itself, but unicell means that a representative volume which represents just one of the multiple repetitions. Okay. Speaking of OFM, well, this is not exactly the same as this fiber arrangement, but we consider this circle as the, we use the octahedral fiber shape so that the analytical solution can be possible, and that's the what we have, and we apply boundary condition to get the stress amplification factors and the equivalent material properties. So given, again, will be a fiber resin property, and output will be applied stiffness and stress amplification factor. Of course, the purpose of this is to predict strength of the fiber and stiffness of a fiber. I mean the resin. I mean the ply. So there are several procedures, and this the paper has been published. Oops. Well, let's see. How come? Okay, well, I'm sure there is some publications, or you can find the micromechanics of a failure. We call theory called MMF, micromechanics of failure for composite, has been published more than 10 years ago. So this is the first ever micromechanical paper published and leading whole micromechanics industry. And you can easily find and download it. For example, all the this paper discuss about the all the theory I just explained to you, and the procedures. Well, this little complicate procedures. There are little simpler papers, but this is not a good one. But there are several papers. Well, you can have a Wikipedia, which introduced the MMF proposed by myself, and you can see, you can go through these procedures. Okay, well, we will back to these procedures, and I just like to emphasize the different method and different concepts. And here, as you can see, we have this is the M matrix, stress amplification matrix, and this is not numerical value. This is the a driven equations in terms of all the geometry and material property and so on. And this is the very interesting result and very useful result. And along with the fiber volume fractions, how these stress amplification factor, for example, M22 value, depending on the region 1 and region 2 and region 3 changings. And then compare with all other method. And as you can see, very accurate compare with FEM. And this is the FEM, dot FEM, and line is the OFM procedures. And this is the failure criterion. Failure criterion means that based on the FEM. See, once you have a stress amplification factors, we can have a failure envelope. And this is the based on FEM, this is based on OFM. Okay. Well, some topics are a little, advanced for those who have no idea about the composite, but we will back to this issue, micromechanics, because the micromechanics is the very important topics, and that's why firstly I cover them so that I give you an idea. Oh, there is a method called micromechanics, and then we will go through all the equations, and we will come back these micromechanics, and I want you to read them again, and I will load this one. I will save as the version 18. Okay, this is the version 18. Okay, this is the version 18, and the please do not distribute to outside. This is only for you and only for students. Do not distribute to outside. I will happily copy this into. I will show you Katalog, and then here I'll just send it to you. All the notes we covered so far. And also I'm recording all the classes so we just been doing for almost 3 hours. And then I really highly recommend all of you to review all the courses, even though you understand mostly, but you need to go through repeatedly so that you can fully understand all the classes. Okay, any questions? I will be happy to hear any questions. Well, I'm not sure why you guys are silent, because your mic is silent or your voice is silent. Anyhow. Okay, if we don't have any questions, Chunghyun, are you there?
네.
Any questions?
그 마이크로 메카닉스로 스트레스 앰플리케이션 팩터를 이제 얻어내서 그거를 이제 호모제나이즈드 물성으로 사용한다고 하셨는데
아니. There are two different.
아, 네.
스트레스 앰플리케이션 팩터를 구한 다음에 스트레스 마이크로 스트레스를 구한 다음에 그걸 가지고 마이크로 스트렝스랑 비교해서 강도를 계산하는 거고.
예.
Homogenized property 구할 때는 스트레스 앰플리피케이션 팩터가 전혀 필요 없고.
아, 전혀 필요가 없는 건가요?
그렇지. 스트레스 앰플리피케이션은 전혀 필요 없고, 우리가 프로시저에도 봤지만은 처음 보는 수업을 듣는 사람, 뭐 다들 처음이겠지만은 조금 컨퓨징이 될 겁니다, 당연히. 근데 계속 생각을 여러분들이 해줘야 돼요. 지금 스트레스 앰플리피케이션 팩터 말고 지금 이게 이펙티브 스트레스를 구할 때는 지금 결국 이게 6x6 매트릭스를 구하는 거기 때문에 우리가 100를 이 바운더리 컨디션에 가하고 이런 유니셀에 가하고 그 다음에 이 반력을 FEM에서 계산한 것이 바로 첫 번째 C 칼럼이고 그 다음에 0일 해서 또 간 게 두 번째 칼럼에서 C 매트릭스를 구한다. 이게 컴파짓의 Homogenized Stiffness이기 때문에 이 계산 구할 때는 Amplification 팩터가 전혀 필요 없지.
네, 이해했습니다.
오케이. 자, again, 지금 이 두 과정이 상당히 아주 중요합니다. 여기에 내가 서머라이즈를 했지만은 요 Homogenized Stiffness 금방 얘기한 거, 그 다음에 Stress Amplification 팩터를 구해서 Strength를 구하는 거, 그 두 가지가 요 하나의 모델 가지고 한다라는 거고, 이 모델을 꼭 이렇게 FM으로 복잡하게 해야 되느냐? 그건 아니다. 요렇게도 할 수 있고 요렇게도 할 수 있고 요렇게도 할 수 있다라는 얘기고 지금 어널리티컬하게 해놓은 것도 있다라는 얘기입니다. 자, 오케이. 타픽이 좀 헤비는 했지만은 이 복합 재료를 이해할 때 이 파이버와 레진의 좀 뭔가 마이크로한 것을 이해하는 게 필요할 것 같아서 마이크로 미케닉스를 먼저 했습니다. 지금 리포트는 이 룰 오브 믹스처, 자 봐요. 룰 오브 믹스처를 가지고 요 물성치들을 얻어내는 거예요. Homogenized 복합 재료의 등가 물성치, 복합 재료의 이제 강도. 근데 여러분 뭐 EX가 뭐고 뭐 X가 뭔지도 모르는데 이걸 어떻게 하냐? 예, 이해합니다. 그래서 내가 한 가지만 구하라고 하겠습니다. 두 가지만 구하라고 하겠습니다. EX하고 EY만 구하라고 하겠습니다. 그 다음에 요 X하고 세 가지입니다. 요 세 가지를 룰 오브 믹스처로 구하자라는 것을 어사인 해주겠습니다. 필요한 물성치는 여러분들이 어슘하면 되고요. 주로 이제 어널리티컬 솔루션이 되겠습니다. 자, 오케이. 자, 지금 4시가 다 됐네요. 자, 토요일 날 항상 수업을 듣느라고 여러분들 수고가 많은데 이왕 듣는 거 복합지를 한번 재밌게 한번 열심히 하면은 요새 자동차니 뭐 항공기니 여러 분야에서 지금 뭐 이 풍력 발전이니 이 복합 재료가 상당히 많이 쓰이고 있죠. 여러분들이 복합 재료를 잘 하면은 아주 전문가가 될 수 있을 거라고 봅니다. 자, 오케이. 오늘 수업 여기로 하고요. 만약에 질문이 있다 그러면은 카톡방에 언제든지 올리십시오. 예? 카톡방에 언제든지 올려서 같이 문제를 시험하도록 합시다. 자, 오늘 수업 여기까지 하겠습니다. 수고했어요. Shoot.